Good afternoon, all. We start the 9th lecture in the series of statistics in research methodology. Before we go to the day's topic, we will have a quick summary of all the topics we discussed in the previous lectures up to lecture 8. Let us note. So initially we started with the the roles of statistics in various facets of life as well as research. Then we later on went ahead with the physical quantities, their measurements and the parameters affecting their measurements, and the way of presentation of results of measurements along with the accuracy and precision of the measurements. In order to effectively represent the results of analysis, how one can utilize the significant figures appropriately, place value of digits, rounding off, and the rules pertaining to each of these parameters. Later on, we had learned the error propagation rules and applied for the propagation of errors during measurements. Then the various types of measurement errors, namely gross, systematic, and random errors, their sources, and the ways to tackle each of these categories. And finally, we concluded that gross and systematic errors could be avoided, could be got rid of completely, but random errors are inevitable during any measurements, and we have to tackle them so that we can minimize them. For understanding the characteristics of such repeated measurements, we had studied the properties of Gaussian distribution function in detail. Later on, we had added the terms confidence level, confidence interval, and confidence limits in order to include the true value within the purview of the repeated measurements and mean value obtained thereof. For completion of the discussion, we had went ahead with the discrete and continuous probability distribution functions, their mathematical expressions, and the required statistical parameters, namely mean and standard deviation for each of the different category of distribution functions. Later on, we learned how to go about the hypothesis testing using Z and T statistics, the various errors which we anticipate, namely type 1 and 2 errors, also known as alpha and beta errors, and the steps to conduct the hypothesis testing in the flow diagram for the hypothesis testing procedure also we had discussed. And in the last class, we had learned that the minimum number of replicate measurements required in order to get reliable measurement data as a function of both the number of repeated measurements, T statistic, as well as the level of concentration or level of the quantity being measured. The optimization of the number of replicate measurements were discussed in the last and previous classes too. Then we had learned what is the reliability interval, whether it is dependent on the number of measurements, the concentration level, and the t-statistic. But later on, we had learned the distribution function of chi-square statistic as well as the F-test in order to verify the whether two such measured populations or measured statistics are having identical variances or not. This was the point we left in the previous class. In the F-test, essentially we do the determination of ratio of variances of the two distributions which we are doing the testing. And the null hypothesis was that both are having identical or comparable variances. Variances are nothing but the squares of standard deviation. If at all we have to do the comparison of multiple variances or multiple standard deviations or multiple properties of distribution functions, the F-test is extended and the name given is analysis of variance, ANOVA in short. Analysis of variance is an extension of the routine F-test, that is variance ratio test, wherein the null hypothesis goes like this. The distributions or the functions which we are testing all of them are supposed to have identical variances. Their means are comparable. The alternative hypothesis, hence, will be at least two of these mu's are having different distribution, measure of distribution. The measures of distribution, there are two types of measures in statistics. One is called a measure of central tendency. It is normally represented in different ways like mean, median, mode, and measure of dispersion. These are generally expressed in terms of standard deviation or variances. So the measures of dispersion are being compared during this variance ratio test. When we are doing the multiple population evaluation, the name goes like ANOVA, analysis of variance. A few of the typical applications of analysis variance are listed here. For example, if a set of analysts, say 5 analysts, are doing the determination of calcium via a particular method, and the idea is to evaluate whether there is a significant difference between the results obtained by the 5 analysts. This can be easily carried out by conducting an analysis of variance, ANOVA test, that we will see later on in detail how it is carried out. The systematic stepwise evaluation of ANOVA will be discussed using this particular example. Further, another 3 examples are also given here. For example, the fluorescence intensities of complex ions are measured as a function of pH. So several different pH values were taken as the points of evaluation, and the fluorescence intensities of certain metal complex are being measured. Whether all these 6 measurements, 6 points of measurements, are they showing same value, or from the measurements whether we can say that S fluorescence intensity varies as a function of pH, or whether it is independent of pH. The conclusion can be made easily by conducting an ANOVA. Another example is that if different combinations of solvents are used for getting the yield of like some particular synthesis is being carried out, and for which different solvent compositions are in the third example, we are trying to evaluate whether the change in the solvent composition will have an influence in the yield of a particular chemical synthesis. 4 different solvent compositions are being tried, whether these have a significant influence, visibly significant influence on the yield of a particular synthesis. So the effect of change in composition of the solvents can be in the third example of application of ANOVA, we are seeing whether the change in the composition of the solvents will have any significant or visible influence on the yield of a particular chemical synthesis. The same can be carried out using ANOVA. For another example in which manganese is determined by 3 different, altogether different analytical methods, whether the results obtained are comparable, similar, identical, or not. This can be done by ANOVA. So taking the first case as the example, we will proceed in the coming slides. Slides are not known. So in situations like this, the population is a function having different values of a common input parameter. The input parameter we call as a factor or a treatment or a group. The input parameter which is controlling the output, we call it as a factor. And the different values of the input parameter which we keep on varying during the set of measurements that are called levels. Normally the levels we do extreme levels, either the lowest possible or the highest or the largest possible, and somewhere in midway. These are the three levels generally carried out. One can go ahead with more number of levels also. As the number of levels increases, you get better clarity of the impact of the factors on the output of your measurement. The factor which is affecting, the parameter which is affecting, we call it as a factor, and the various values which it assumes during the measurement, we call them as levels. So factor and level combinations will give you an idea regarding the estimate of the change in the output. These terminologies we will be using in the future lectures also. So keep in mind these two terminologies, factors and level. Factor is the parameter which is controlling the output. Level is the value which it assumes during the measurements. In determining, for example, calcium by volumetric method, the first example given above, the factors are the different analysts. Factors are the analysts. And the levels of this factor are, we are conducting the experiment with 5 analysts. So there are 5 levels, 1, 2, 3, 4, and 5, named as the analysts. 5 different analysts. These are the 5 levels of the factor, namely analysts. Then what we do is we compare the output or the measured value, or if the output is another way called response. Then we note down the response and the change in the response as a function of change in the level of each of the individual input factors. Finally, what we do is we compare the value calculated with the tabulated value and arrive at the conclusion. In the case of calcium determination, the response is the number or the number of millimoles of calcium or the concentration of calcium determined by the analyst. So definitely, as the analyst changes, there will be finite change in the response function also. So you can see the millimoles of calcium determined by all the 5 analysts may be varying. Here we can say that the factors are independent variables. When we do construct a calibration function wherein we take y is equal to mx plus c, then the x or the input parameter, input variable, that we call as factor. And the output variable y, which is changing as a function of the input parameter, that is the response. Then obviously the factor is the independent variable and response is the dependent variable. Essentially, in ANOVA also what we do is we compare the variations between different factor levels. When we were conducting the F-test, it was simply taking the ratio of individual 2 variances, and the one which is having higher numerical value was taken on the top, on the numerator. Here we are comparing several factor levels. So factors also change, and sometimes levels also change from 2 to 3 to multiple levels. So as the number of factors and the number of levels increases, the complications start increasing. So one has to go from pen, paper to calculator to computer to some statistical software in order to conduct the entire ANOVA procedure. We will see how the ANOVA analysis of variance is conducted, how the evaluation table, it is called ANOVA table, evaluation table is constructed, and how one can easily infer from the table what will be the outcome, what will be. Generally the null hypothesis goes like this, that there are no differences in the statistical variation of individual input factors. Variation in the output as a function of the input factors. As we have discussed in the previous slide, these are the 4 different examples for the utility of ANOVA. And each of these examples, what are the factors? From the statement of this problems, one can pick out what are the factors, what are the levels, and what would be the expected response or the outcome. For example, in the first case, the analyst is the factor, and since there are 5 analysts involved in the entire measurement process, the levels are from 1 to 5. And whatever we measure, whatever number we get as a result of measurement, that is the concentration of calcium in millimoles of that element, that is the response. What we see is the change in the response function as a parameter as varying with the factors, different levels of the factors. With each individual analysis, definitely the value will be mostly different from one another because there will be always a random variation in the measurement, even though you are able to get rid of the gross and systematic errors. And in the second problem, wherein the fluorescence intensities were measured as a function of pH in different levels, we see that there are 6 different pH levels. So the factor being pH and the levels are the ones which are numbered 1 to 6. The value may be from 0 to 5 or 1 to 6 or whatever value. They are numbered numerically 1 to 6. And the measured response function will be the fluorescence intensity. And in the third problem, the solvent composition is the factor being evaluated or investigated, and the compositions numbered 1 to 4, they are the 4 different levels. And the synthesis yield of the chemical or the compound or the particular material is the response function. And in the fourth problem here, written over here, the determination of manganese by 3 different analytical methods. The analytical methods are the factors, and the three numbered 1 to 3, they are the levels, and the concentration of manganese in whatever unit we express, maybe ppm, parts per million or parts per billion, depending on the context, will be the response function. In the case of the first example, wherein calcium was determined by 5 different analysts using some volumetric determinations, here this graph, this picture represents the values obtained by each of the 5 analysts. Each analyst has done the determination in triplicate before reporting each of them. So the triplicate values are represented by shaded triangles, and the area, the value response values are marked in blue shades, so that you can easily identify the domain or the response region of the calcium values expressed in millimoles obtained by the 5 analysts. So you can see that between the 3 values obtained by each of the analysts, there is a fair agreement between those values, except the fourth one, where you will see slightly larger range. Even in the first one also, the range is visible. If you compare the performances of these 5 analysts, you can say that in the picture on the right side in the screen, you can see the average values obtained by each of the analysts is given by black shaded circles and represented towards the end of the right end of the figure, and the blue shaded region along with the shaded triangular points represent the outcome or the calcium concentrations determined by each of the 5 analysts. So there you can see that there are 15 triangles, that means 15 such outputs obtained by 5 analysts, because each analyst is doing 3 replicate measurements. Total 15 values are there, and each of the 3 values by individual analysts are taken, and their average and standard deviation can be calculated. And standard deviation, when you square, becomes the variance. What we compare essentially is the variances of each of the individual contributing factors. And the variation between the group is closer to or visibly agreeing with the within the group, within the factor, group or factor. These terms are used interchangeably in these slides. The basic statistically we do the test for this thing, variance ratio, which is essentially the F test. In ANOVA also, it is an extension of F-test only. Null hypothesis, as we have mentioned repeatedly, it is nothing but the variances are identical. That is the null hypothesis. When the variation between the group is larger than that obtained within each of the individual groups, then the null hypothesis is rejected. Otherwise, the null hypothesis stands valid. So a large value of f compared to the critical value, now that you have learned enough regarding the f test, you know how to read the f table, tabulated values or the critical values at certain specific significance level. You can easily compare the calculated f value with that of the tabulated one for the specified significance level and corresponding to each of the degrees of freedom for numerator as well as the denominator. That way we come to the conclusion, if the calculated f value comes out to be less than the critical f value, we accept the null hypothesis, else we reject it. How to go about the ANOVA? It is a simplest case where we do single factor analysis of variance. When we have multiple factors, as I told you, when we have two factors, that also can be done by pen and paper. When we have more than two factors, you may have to rely upon Excel or some computer calculations to that. Furthermore, if you increase the factors as well as the levels of each of the factors, you will see that you have to set up combinations of factors with all the possible levels of individual factors. Then the calculations, though simple, becomes a bit involved. You may have to take help of some software packages also. Those things we will see later on. The null hypothesis is that the means are identical. Then if you say if you have such populations, such factors, the means of each of these I factors will be x1 are designated as, normally means are designated by giving an upper bar for the individual values. And the variances essentially we represent as squares of standard deviation, and the subscripts 1, 2, 3, 4 represent the different populations 1 to I. Once we are comparing such I factors in various levels, say J levels, you can have a grand mean and the individual variation in the individual means. Then what we do is shown in the stepwise evaluation procedure in these slides. We can calculate the grand mean. This slide and the forthcoming slides give you the idea. Stepwise evaluation of the single factor ANOVA is given here. You can easily follow these steps whenever you are applying for your set of research data. What you have to do is arrange the mean values and their corresponding input response factors in tabular form. You have the mean value, standard deviations, and take the squares of standard deviation ready for further evaluation. One can easily calculate the grand mean by taking the average of individual input means, like x1 bar to xi bar. So double bar is given in order to separately identify it as a grand mean from the other rest of the means. Grand mean can be calculated mathematically. That is a very simple stepwise evaluation. Grand mean can also be taken by taking the sum of all the individual parameters and dividing by the total number of experimental points. That is, either way you land up in the same grand mean value. And each of the factors, as I told you, will not essentially be in coinciding exactly with the grand mean. There will be slight differences between these values because random variations are always associated with repeated measurements, essentially when we are doing continuous variable determinations. What we do during the sum of the squares due to factors determination is take the difference between the individual mean and the grand mean and square it. It is almost more or less similar to the calculation of standard deviations you do when you do manually. Then you take like individual, whatever be the number of individual means, take the sum of all those things after squaring each of them. Then similarly, in order to, in this ANOVA calculation, two factors are involved, two input parameters. One is the sum of the squares of the factors, another one is the sum of the squares of the errors. Factors, as I told you, the input parameter, which is affecting the output or the response. And the error is essentially the agreement within the individual measurements of a particular factor, within the factor variation. Another name is within the factor variation for SSE, sum of the squares due to errors. The calculation mathematically is done as shown in the second equation in this slide. Essentially, the total variation will be nothing but the sum of the squares of the factors plus sum of the squares of the errors. That is called a total sum of the squares. Total variation or variance, SST, total sum of the squares of the variations is equal to sum of the squares of the factors plus sum of the squares of the errors. Okay. And the degrees of freedom. Essentially, when you are doing the evaluation of any statistical parameter, degrees of freedom should be well known so that you can easily compare it with the tabulated data. If we have n such measurement outputs, the degrees of freedom will be n-1 unless there are no other conditions imposed on the output parameter. If at all any condition is imposed in relation to those many number of conditions, the degrees of freedom keep decreasing. Then there are a few assumptions, two main assumptions made during the analysis of variance. These two you have to keep in mind, that the quantities or the response functions being compared are having almost comparable variances. When I say comparable variances, it is nothing but roughly you can say that the largest standard deviation which is being evaluated should not be more than the double of the smallest standard deviation which is being evaluated. So the range of the values of standard deviation will be within, like if you take the ratio of largest to smallest, will be less than 2. In those cases, this analysis of variance evaluation via this stepwise procedure becomes valid. Otherwise, you may have to impose certain conditions and make the parameters comparable. Else, you may have to do stepwise evaluation procedure in such cases. Another assumption is that as we discussed in the previous classes also, random variation or natural variation follows Gaussian distribution function. If at all they do not follow the Gaussian function, the assumption of Gaussian characteristics, Gaussian curve characteristics, we cannot extrapolate over here. Then we may have to go for other distribution, or else if it is not following any particular distribution, we may have to do distribution-free ANOVA procedures also. Then the evaluation steps becomes a bit more. You have to do it carefully. When we are imposing certain limiting conditions, you are restricting the variable to be within certain range, which is under your control. So the stepwise evaluation procedure becomes handy. Whenever we are releasing the limiting conditions, we have to keep in mind that the variable can have any value, starting from -infinity to +infinity. So you have to account for that much larger variation in the observed measurements. So the number of degrees of freedom, as I told you repeatedly, should be very well understood in order to do this any statistical evaluation. For the total sum of the squares, the number of degrees of freedom, as we discussed in the previous slide also, it is n-1. Since there are I groups of such factors, then the sum of the squares of the factors, since there are I such factors, the degrees of freedom for these factors will be I minus 1. And each factor will have, say, some particular level, number of levels. The degrees of freedom for the particular number of levels or the error factor or within group variation, that will have the degrees of freedom as mathematically shown over here, n minus n. N is the capital N is the total number of measurements, outcomes, and n minus 1 is the degrees of freedom for the total sum of the squares, and I minus 1 is the degrees of freedom for sum of the squares. N minus I is the degrees of freedom for the sum of the squares of the errors. SSF, SSE factors, how we calculate, that we have seen in the previous slide. Now, if you divide each of the factors, each of the parameters on the right hand side of this equation with the corresponding degrees of freedom, you get the mean value. Almost similar procedure as we did for the standard deviation in routine 9th, 10th standard calculations. So by dividing the sum of the squares by their corresponding degrees of freedom, we get the standard deviations within we get the mean value, means factors corresponding to these different input parameters. So the mean square due to factors level, it is in short form written as MSF, is nothing but the sum of the squares of the factors divided by the corresponding degrees of freedom, that is I minus 1. MSF is SSF divided by I minus 1. Similarly, the mean square due to errors will be sum of the squares of the factors divided by n minus I. Then the essential test statistic here also goes about like this, the F value, the variance ratio. Then here the F value is given as MSF by MSE. So the quantity MSE is almost a representative of the variance due to the error factors, because within the factor, within each level of the factor, what is the variation? And MSF is a combination of both the estimate due to error as well as the variation between different groups or different factors. So it is a sum of sigma E square and sigma F square. If the sigma F or the factor values between groups variation is small, very small, negligibly small, then what happens? The sigma E square, within factor or within the level of variation will be almost equal to the between group variation. That means the F value calculated will be almost near to unity. That means between groups variation is negligible compared to within group variation. That is what the ideal case would be. We are getting F values very close to unity, as we have seen in the variance ratio test also. If the factor effect is significant, that is the alternate way, then you will see that MSF would be greater than MSE. That means the black dots, black circles shown in the previous slide, they will be varying very largely compared to the shaded triangles. To complete this hypothesis test, what we do is, after calculating the F value, we compare it with the corresponding critical values of F for specified significance level. If it is not specified, we go for 5% significance, nothing but 0.05 value of alpha. If calculated F value exceeds the critical value, we reject the null hypothesis, else we retain the null hypothesis. So generally, once you do the entire steps of evaluation of analysis of variance, the final results are tabulated and presented to the reader or the audience in this form, wherein we do between group variation, within group variation, which are represented as SSF, SSE respectively, total sum of the squares as SST. The short forms written over here on the right, second column, those will be replaced by the corresponding numerical values, as the case may be. I will be the number of levels of each of these factors, I minus 1 degrees of freedom will be given numerical value, n minus I again degrees of freedom for the within group variation. N minus 1 is the total number of degrees of freedom for the total sum of the squares. Then MSF, MSE are calculated. Finally, we go for the calculation of F value and then compare with the critical values reported in the table for corresponding to the level of significance as well as the degrees of freedom. Degrees of freedom are already tabulated here. So one can easily take the data from here and compare. Only thing you have to keep in mind is the significance level. If not mentioned, go for 5% significance level. And there are differences when we are doing two-way analysis of variance, go for that two-tailed table. If we are going for one-way analysis, go for one-tailed F table. The same example we used for understanding the analysis of variance by the stepwise procedure. The values are given here. Let us try to attempt this problem. 5 analysts have determined the calcium by volumetric method and obtained the amounts of calcium as shown in this table. Do these values differ significantly at 95% confidence level or not? How do we do? The whatever we have learned in theory, let us apply over here and see. First, what we do is we calculate the mean, individual means, as well as the standard deviation. The regular procedure means one can do easily. The values are already given. All of you may give a try on your own without checking the answers directly. Then, as we discussed in the previous slide, we can calculate the grand mean via the simple formula as discussed in the previous slide also. Then the sum of the squares of the factors, the formula given in the previous slide is directly used with the data, numerical data over here. Substitution of numerical values only is that as there are 5 analysts, the number of degrees of freedom for the between group variation, sum of the squares of the factors will be 5 minus 1, that is 4. And when within the total number of measurements will be 5 into 3, since each of the 5 analysts is carrying out 3 replicate measurements, we have 5 into 3, 15 measurements in total. So within group sum of the squares, that is the sum of the squares of the errors, SSE, will have degrees of freedom corresponding to n minus I, that is nothing but 15 minus 5, that will come out to be 10. The steps which are described in the previous slide are exactly followed only by giving the numerical values. Then we can calculate the MSF by dividing the SSF with the number of degrees of freedom, and MSE again by the corresponding degrees of freedom are taken in the denominator. Then the F value is calculated by taking the ratio of MSF to MSE. Here the value comes out to be 20.68 in this numerical problem. The presented analysis of variance ANOVA table would look like this in this problem. Do not do the rounding off at any of the individual steps. Keep the digits as many as possible during the entire calculation. Rounding off should be done only at the end. That is why we have discussed the importance of rounding off in the very beginning of these lectures. Furthermore, we see that the degrees of freedom for the numerator is 4 and for the denominator it is 10. The value of F will be around 3.48 in the corresponding F table. Then we can see that like here the comparison is done at 95% confidence level, and the degrees of freedom for numerator and denominator are 4 and 10 each respectively. The value is critical value of F is 3.48, whereas the calculated value of F is 20.68, which is substantially larger than the critical value. Then we reject the null hypothesis. That means there is a significant difference between the values obtained by the 5 different analysts. Then which analyst is going wrong? That we can do by another test, and we can keep it as an outlier and go ahead with the F test and finally refine the data and come out with improved quality data later on in stepwise evaluation. So that way we can either include or exclude some input parameters, input values or input factors and go ahead to get cleaner, reliable data. Now we go ahead with another statistic, namely product moment correlation coefficient. Everybody knows the formula for that. It is nothing but the quotient of covariance of two functions, dependent and independent variable, divided by the product of their standard deviations. Generally, the variation in the product moment correlation coefficient is shown in three different cases. One is that a perfect correlation between the dependent and independent variable. Then we see that R value, correlation coefficient. Some people use the word Pearson's correlation coefficient. The same thing. The correlation coefficient R value will be +1, where we see that there is a perfect positive correlation. As and when X increases, Y also increases linearly. So this is a case of perfect positive correlation between X and Y. Then as and when X increases, Y decreases linearly, then we see that the R value, correlation coefficient R value will be -1, exactly -1. The value may lie in between of these two extremes also, provided the dependency is not perfectly matching with each other. If at all there is no correlation between X and Y, the change in Y is not dependent on that of X, then we see that the correlation coefficient R becomes almost near to 0. So as and when R approaches either of the extremities, then you say that there is linear correlation, either positive or negative linear correlation. But R value is not only the parameter which decides, that we will see later on. All of you can easily do the calculation. The R definition, mathematical expression is given here. All of you can do this calculation to find out the correlation coefficient during the measurement of fluorescence intensities using some device spectrometer. The values are given in some arbitrary unit of the fluorescence intensities. Normally absorbance or the emission units are used. Concentrations are also given. You can do calculation. I will show you the stepwise evaluation, how the correlation coefficient is calculated. X is the input parameter concentration, fluorescence intensity is the Y parameter. Using the mathematical expression shown in the previous slide, you can easily calculate the correlation coefficient. It will come out to be around 0.9989. That is a positive value, very near to 1. That means almost very good positive correlation between the fluorescence intensity and the concentration of the input parameter. Here, during the calculation, one can have a self-check wherein you see that the sum of the differences between the individual value and the mean value. Xi values are the individual value, mean values are represented by bar, X bar or Y bar. You will see that the sums of the input as well as the measured values, you see that sums are almost always comes out to be 0. It will be a cross check for you to do while carrying out the calculation of the correlation coefficient. Sigma xi minus x bar comes out to be 0. Again, this also sigma yi minus y bar also comes out to be 0. So if you are getting the 0, well, that means your calculation till that point is correct. This is a similar problem for you to do the calculation yourself. I have not shown the individual calculation steps of calculation directly. The answer is given. Okay. So you see that the rounding off is not done till whatever digits you get in the calculation. All the digits are shown. Until you take the final conclusion, rounding off, please do not do the rounding off. For you to get familiarization, you can have the plot of this absorbance versus concentration curve and see whether it is linear or whether it follows a polynomial function. Using appropriate software, you can do. These are very simple. You can easily do, even take help of Excel also. While while reaching to any conclusion with the basis of correlation coefficient, you should be very careful that even sometimes quite poor looking calibration plots give very high R values. So not only the R values, visual or graphical evaluation of the functional relationship is also important. Generally, R values are taken for whether there is a linear relationship or not. Sometimes the R values may mislead us because numerator and denominator may be numerically almost comparable, but the relationship may not be perfectly linear. So adequate number of significant figures you have to keep. Do not do the rounding off at any of the individual steps during the entire process. And the figures, if you round off, what happens? If you round off this 0.991 to the nearest first decimal or second decimal, it comes out to be 1, which may mislead you that there is a perfect linear relationship, but there are small changes which should be given due importance during the entire calculation if it is only a part of several steps of measurements. For example, here two such cases are shown. If you just put the R, calculate the R value for the figure A, it comes out to be 0.986. Whereas for figure B, you see that the R value comes out to be 0. It doesn't mean that in the case of figure A, it shows the linear relationship, and in the figure B, the values do not have any relationship at all. It is not, we cannot conclude just by seeing the R value. You see that the figure A can be better fitted to a polynomial function rather than a linear function. So if you do graphical evaluation or software evaluation, you will see that there are better suited relationship for some functions wherein R is not the only deciding factor to take final conclusion. Whereas in figure B, you see that even though they are not linearly related, as x changes, as x increases, y has got some maybe some parabolic function is there. So you have to visually see and evaluate via alternate procedure before concluding about the quality of the data. Sometimes you may miss out some important input parameter from this plot, which you just see the R and take a conclusion. So wherever possible, try to analyze your research data to the maximum extent possible, not only physically by taking help of any software available till time. As I told you, the correlation coefficient alone cannot give us the final conclusion. Another way is to do the evaluation via the t-test. This t-statistic is alternatively represented by the equation shown over here. Here, the null hypothesis is slightly different compared to the earlier ones. Earlier, when we have small values or very low values of R, we propose the null hypothesis as that there is no correlation between X and Y. Earlier, whenever we were proposing the null hypothesis, we had kept that in F test and the T test and the Z test, that they are perfectly matching. Here, the null hypothesis, if you put the other way around, again the conclusion will change. But here, in most of the references, you will see that the null hypothesis is proposed whenever the R values are low, that there are no correlation. From the R, we infer that there is no correlation between X and Y. But we are not very satisfied with the conclusion. Now, in order to see mathematically, numerically, whether the conclusion is correct or not, what we do is we evaluate via the t-statistic. T-statistic is calculated using the expression shown over here. As you can see, if the t calculated comes out to be greater than the t critical, the degrees of freedom will be n-2 because we are using some linear relationship wherein the functional inputs like the coefficients of x and the intercept or the numerical value. There are two inputs, so the degrees of freedom comes out to be n-2. Keep in mind, when we are doing the t evaluation for correlation between linear correlation between two variables, the degrees of freedom is n minus 2. Whereas in the other cases, we had seen that the degrees of freedom was n minus 1. Here, one more condition is imposed on that they have a linear relationship. One more condition. As the number of conditions increases, not proportionately, accordingly, the degrees of freedom keeps on reducing. If at all the t calculated is greater than the t critical, the null hypothesis is rejected. That means if t calculated is higher, we say that the correlation is significant. We can see that as the R value is closer to 1, the numerator value increases and the denominator is also decreasing. Denominator decreases, numerator increases. Essentially, the t value increases, which will be favoring the correlation, favoring that there will be correlation. That is rejection of the null hypothesis, that they are significantly correlated. The input or the dependent and independent parameters are correlated significantly. That's all about the correlation coefficient. You can have practice of correlation coefficients. You might have, several of you might have done already. Now we go ahead with the line of regression of the variable y on x. Here, this line of regression is utilized in the calibration of instruments and several of the equipments during analysis. Here, the assumption is that the errors or the variation in the y are only significant. Errors in the x are negligibly small, so we avoid. Even though this is not exactly the true case in real situations, the presumption based on which we do simple linear regressions, where we take that y is only varying. The variation in y is only visible. And in the y direction errors, there are two sources of this y direction error. One is due to the random variation in the measurement, which we call as experimental error or random error about the regression. The second one is that when we impose a regression line, the linear relationship of regression lines, due to the forcibly overlapping or forcible overlapping of the observed data with the assumed linear function, we see that there is a natural inherent change in the instrumental signal, measured signal. So that is called a variation or error due to regression. Two types of errors. One is variation about the regression, another one is variation due to regression. These are the two sources of errors when we apply the line of regression of a function on an independent variable. In the case of a straight line graph, we see that the regression coefficient R square becomes equal to the square of the correlation coefficient. But this regression can be applied not only for straight lines, it can be applied for polynomial functions or quadratic functions or any other function of higher orders. When we do the least square fit, the linear regression, we essentially follow the least square parameters, where we initially impose some certain conditions, where we say y is a function of x as y is equal to mx plus c. Then we derive the value of m and c by iterations wherein the distance or the difference between the observed and the functional mathematical or theoretical values differences are as small as possible. What we see that the squared differences, squares of the difference between vertical difference between the measured and the calculated values, we minimize it. We try to minimize them and make it the least possible. Squared differences, we make it the least. So that is why the method is called a method of least squares. However, all data do not fall exactly on the least square line because random errors are inevitable during any experimental measurement. Then what we do is we try our best to fit the best straight line wherein the squared distances are minimum. So in order to do that least square line, what we do is we apply the method of least square and do iteration so that the sum of the squares of the distances are minimum. All of us know how the basic linear least square fitting is done for a relationship of the sort a y is equal to a plus bx, where a is the intercept, b is the slope. The intercept and slope can be calculated mathematically as shown in the equations over here. Intercept a and slope b of the least square line can be calculated, and the fitted line values. Normally, they are given this gap in order to separately identify them. The difference between the vertical difference between the least square line and the measured value. Measured value is taken initially, then the fitted value on the right side. Yi, measured value minus the fitted value. A plus bx is the assumed linear relationship. So if you take the difference between the measured value and the fitted value, measured value first, then the fitted value, that is called the residual. Idea of least square fitting is to minimize the residual and get the functional relationship as closely mimicking to the measured experimental value as possible. So the regression, if you impose this condition, then you see that the regression line must pass through the centroid of the set of points given in that experimental range. So we can calculate the y direction errors during this fitting. This fitting is done using any software. Nowadays, people use software only to do this calculation. Earlier, manually people were doing. The y direction error can be calculated via this equation, wherein the capped function represent the fitted value and the subscript yi represent the measured or the observed parameter. As I told you, since it is a linear function, the degrees of freedom linear function with the two input parameters, intercept and slope, defined altogether, well defined, then the degrees of freedom comes out to be n minus 2, where n is the number of data points, number of input points. Okay, the cap values are the fitted functional values. The difference between the measured and the capped function, the square and sum, and then when divided by the number of degrees of freedom and the square root is taken, it is the y direction or the vertical direction errors during the regression function of an observed parameter y, which is a function of x. Now we can calculate the standard deviation of the fitted slope as well as the intercept, and essentially from the standard deviation of the slope and intercept, we can calculate what will be the error associated with the concentration if you are using similar type of calibration function to derive the concentration of an unknown input parameter. You can calculate the confidence interval, confidence limits also, confidence intervals for the slope intercept. So once you construct a particular calibration curve, y is equal to mx plus c, we can predict what is the range of variation, what is the variation in both the intercept as well as the slope of this functional relationship, so that the reliability of your calibration function is visibly seen. Here, using the data given in the previous question also, you can calculate the slope as well as the intercept of the regression line. Easily we can calculate, or we can use help of any software also. Finally, then using the relationship shown here, standard deviation for slope as well as the intercept, you can calculate the standard deviations of each of these parameters and further calculate the confidence interval. There's nothing but if the slope is given as b, then the confidence interval will be b plus or minus t times the standard deviation of b. The confidence interval for intercept will be a plus minus t into the standard deviation of a, where a is the intercept. So that way, all of you may give a try to get the values of the slope, intercept, and the standard deviations of each of these two. Further, later on, you can calculate the confidence interval of these parameters also. The answers are already given here in these slides. Once you have done with the entire calculation, you can see whether your values are matching with what is reported. As there are 7 such data points, you can see that the p-value for 95% confidence level for 5 degrees of freedom is 2.57. That way, we can calculate the mean value of the slope plus or minus that corresponding t value. It is 2.57 from the table. So that way you can calculate the slope, confidence level, limits of the slope. Similarly, intercept and the confidence limits of the intercept. Since there are n is equal to 7, n minus 2 comes out to be 5. So you have to read the t table as for 5 degrees of freedom. If not mentioned, we go for 95% confidence level. This problem, all of you may please try. The answer is directly given here. A few measurements were done for silver standard solutions by flame atomic absorption spectrometry. You can calculate the slope, intercept, and the confidence limit as we had done in the previous question. Confidence limits of the parameters, calibration parameters you can do. The answers are given directly over here. You may give a try. In the next slide, the steps of the answers are given. Steps of the deriving the answers are given in the next slide. I'll just show you the next slide, but all of you do independently. The confidence level is taken for a t value of 2.57 since there are 7 values for 5 degrees of freedom. At 95% confidence level, we have to read the t table and take the critical value from that. And here, since the values are individual measurement values, we take x plus minus ts. The denominator root n is not taken because these are individual input parameters. Whenever we had x bar, we went for x bar plus minus ts by root n. Since it is only x values, we go for x plus minus ts. So we stop here for the day. You all give a try to get the calculation of confidence limits of intercepts and slope. In the next class, we will discuss further similar way confidence limits of the concentrations which are calculated on the basis of the calibration curve constructed in similar way. That we will see in the next class. We stop here in this slide. Any doubts are there, you please write down in the chat box. Otherwise, I'll summarize over here. We had started today's discussion from the extended F, that is analysis of variance ANOVA. A few examples were taken and defined the factors, levels, and the response parameters, the degrees of freedom for each one, the stepwise evaluation of ANOVA, sum of the squares of the factors, sum of the squares of the errors, degrees of freedom, and the F values as F by MSE, then compared with the critical values of F corresponding to that specific number of degrees of freedom and significance level. Then we went ahead with worked out example and did a separate one. Further correlation coefficients were discussed in short. Then the line of regression of Y on X. Further, the errors, the sources of errors during this regression function, the standard deviations of slope and intercept, and the confidence limits or confidence intervals of these calibration functions. Here we stop. Tomorrow with the other class, we'll discuss the confidence limits of concentration from these calculations. If there are any doubts, let us just have a check on the chat box. As there are no doubts, let us wind up for the day. See you all on Wednesday.